Example 3, the member shown in the figure is pin connected at A and rests against a smooth support at B. Determine the horizontal and vertical components of reaction at the pin A. So if you can observe, our loading is uniformly varying, and we already did this, right? So we can now calculate for the equivalent single load of this uniformly varying loading. So we redraw our free body diagram. Okay, so we have, it looks kind of like this. Yeah, and then, okay. We have, of course, we can represent this one as a single force. Let us call that F sub R. Okay. And then we have for our smooth support at B, it must be that it is perpendicular to our AB part of our structure, right? Because it kind of look like this one. It supports this part of the structures. It means cannot. Ayun. And since it says here that our point A is pin connected, so we have our horizontal, our vertical. Oh wait, let me change this color here to red. Okay. Ayun. We have B, and then we have A sub Y. And just like what we did by inspection, we can observe that only our B, which is the force that our support exerts to our rigid structure, has an X component, and it is going to the left. So therefore, our A sub X will be to the right to resist that force. To the left, to the right. Now for our F sub R, we'll calculate it as F sub R is equal to the area of our loading, and our loading follows a triangular loading, so that is 1/2 base times height. Now our base is the length, the length, which is 1.5 times 1.5 times the height of our triangle, which is the maximum loading at the very end, that is 80 Newton meters. So that's 80. So therefore, our F sub R is equal to 80 times 1.5 divided by 2, and that is 60 Newton. And it acts, now if we measure it from A, that is from the tip, so that's that's 2/3. So this is bar X is equal to 2/3 times 1.5. So bar X is equal to 1.5 times 2 divided by 3, and that is 1 meter from A. So this is, we have going down, which is 60 Newton, and we have a clockwise moment at the very end, which is 90 Newton meter. So we provide our dimensions now. So this here is 1 meter. Okay, but this one is 1.5. Okay, the length of AB is 0.75, right? And this angle here is 30 degrees. Oh, let me rewrite that. 30 degrees. And again, our B is applied perpendicular to our AB, right? Okay, because so if that is if this is 30 degrees, it means that this part here is also 30 degrees, right? Because if we draw a horizontal, this part is 30, this part is 60 degrees. It means at the very top, that's 30 degrees. Okay, so if we do uh, our equilibrium equation, summation of forces x or summation of forces y, we have two unknowns again because we will have b sub y and a sub y for summation of forces y, and two unknowns again for our forces x, that is a sub x and b sub x. So the best thing that we're going to do is we do moment summation, and where that would be at our a. So we solve summation of moment about A is equal to 0, assuming counterclockwise positive. And again, just like what we did sa moment moment, couple moment, if we have this kind of provided in our structure, we just have to add it in our summation. And of course, it must follow our assumption. If it follows our assumption wherein we assume counterclockwise positive, then it will be positive. If it is clockwise, then it will become negative. Okay, so if we do moment summation, assuming counterclockwise positive, B will be positive, right? And again, our B is applied perpendicular to our structure AB. So therefore, this is B times our its perpendicular distance, which is 0.75, right? And then the remaining forces is clockwise, 60 times 1 and 90 Newton meter. So that is minus 60 times 1 minus 90 is equal to 0. So this is B times 0.75 is equal to 60 plus 90 is equal to 150. So B is equal to 150 divided by 0.7, and that is 200 Newton. That is the force exerted at B, meaning the amount of support that our point B must give to our rigid structure, to our structure to make it a rigid one. Okay. Then we do summation of forces x is equal to 0, assuming to the right positive, right? Now, again, our a sub x is going to the right, so this becomes positive. So a sub x, and our b is going to down to the left. So we can either use the 30-degree angle above or our 60-degree angle. It depends. Now, if we use our 30-degree angle, we will be using b sine 30 degrees for our x. So that is, let us say I will use my 30-degree angle. So that is b sine 30 degrees is equal to 0. A sub x is equal to 200 sine 30 degrees. So A sub x is equal to 100 Newton. Now, if we do summation of forces y is equal to 0, assuming upward positive, so that would be A sub y minus B cosine 30 degrees, and we have one more force, and that is 60 going down. So that's minus 60 is equal to 0. So A sub y is equal to 60 plus 100, that's 200 cosine 30 degrees. So our A sub y is equal to 200 cosine 30 is 173 plus 60. That's 233.205 Newton. Okay, that is example number 3.